Right now, more than 25 billion kilometers from Earth, a machine built before the first personal computer is listening to a sound no human ear could ever hear. Voyager 1 is moving through interstellar space, beyond the protective bubble blown by the sun, carrying a transmitter weaker than a refrigerator light bulb and a computer system with less memory than a cheap digital watch. Its signal takes almost a full day to reach us. By the time Earth answers, another day has nearly passed. And hidden inside that impossibly faint stream of data is something strange. Not a message, not an alien broadcast, not proof of a secret object waiting in the dark, something quieter. Voyager 1 has detected a thin, persistent vibration in the electrically charged material between the stars, a nearly continuous tone buried so deeply in the noise that scientists had to filter years of measurements to reveal it. The tone rises, it falls. It changes as the spacecraft moves, and those changes are allowing researchers to do something that had never been done before: trace the density and turbulence of interstellar space almost continuously from inside the medium itself. To put that in perspective, imagine walking through a pitch-black house with no camera, no flashlight, and no map. All you have is a wine glass. You tap it, listen to the pitch, and from that tiny ringing sound, you work out the shape of every room. That is roughly what Voyager is doing between the stars. But the deeper mystery is not simply that interstellar space has a hum, it is what seems to be producing it, why the density outside the sun's boundary changed so dramatically, and how disturbances from our star can still reach Voyager long after the spacecraft has crossed into another physical environment. Almost nobody thinks of interstellar space as a place with weather. The headlines usually describe it as empty, silent, and still. It is none of those things. Stay with me, because by the time this is over, you will never think about the silence between the stars the same way again. Before we follow that faint tone into the dark, subscribe and turn on notifications. Let's go back to the beginning. On September 5, 1977, Voyager 1 lifted off from Cape Canaveral aboard a Titan III-IE Centaur rocket. The original mission was bold but clear: fly past Jupiter, continue to Saturn, study their moons, rings, magnetic fields, and atmospheres, then keep going for as long as the spacecraft survived. No one launching it that morning expected the probe to remain scientifically active for nearly half a century. Voyager 1 was not designed around modern processors, cloud storage, or software updates delivered through high-speed links. Its electronics belonged to an era of magnetic tape, analog instruments, and computers with tiny amounts of memory. Commands had to be compact, data rates were limited, every watt mattered. Yet the trajectory was extraordinary. Voyager 1 reached Jupiter in 1979 and returned images of a system far more violent and complicated than expected. It helped reveal active volcanism on Io, photographed turbulent cloud structures, discovered a faint ring around Jupiter, and transformed distant moons from points of light into geological worlds. Then came Saturn in November 1980. The spacecraft examined the planet's rings, moons, atmosphere, and magnetic environment. Its close encounter with Titan bent its trajectory sharply northward, lifting it out of the plane where most planets orbit. That choice ended any possibility of sending Voyager 1 onward to Uranus and Neptune. At the time, it looked like a sacrifice. In reality, it gave Voyager 1 a path no other spacecraft had taken. After Saturn, the probe entered a long outward climb. The planets fell behind. The sun became smaller. The spacecraft's cameras were eventually switched off after the famous 1990 family portrait that included the pale blue dot image of Earth. The visual mission was over. The invisible mission was beginning. Scientists wanted Voyager 1 to search for the outer boundary of the heliosphere. If you have never heard that word before, think of the heliosphere as a vast, irregular bubble created by the solar wind, the stream of charged particles flowing outward from the sunday. That wind carries the sun's magnetic field with it, inflating a protective cavity inside the surrounding interstellar medium. For years, researchers knew this boundary had to exist. They did not know exactly where it was. They did not know how thick it would be. They did not know whether crossing it would look like passing through a clean wall, a broad swampy region, or a shifting series of layers that moved as the sun changed. Voyager 1 would have to find out by touch. Here is where the first twist arrives. Scientists expected the spacecraft's transition into interstellar space to be obvious. The solar wind should weaken, particles born inside the heliosphere should fade, galactic cosmic rays coming from outside should increase. The surrounding plasma should become denser, and the magnetic field might change direction as Voyager moved from a sun-dominated region into the magnetic environment between the stars. Some of those signals arrived exactly as expected. Others did not. On December 16, 2004, Voyager 1 crossed the termination shock. That is the region where the supersonic solar wind abruptly slows because it begins pressing against the material outside the heliosphere. Imagine a fast river hitting a massive obstruction and suddenly piling up, churning, and losing speed. Beyond that shock lay the heliosheath, the outer layer of the sun's bubble. Voyager spent years inside it. The region was messy. Particle intensities rose and fell. Magnetic fields strengthened. The outward flow of the solar wind slowed until, in Voyager's direction, it nearly stopped. Researchers began watching the data for the final crossing, the heliopause, where the sun's particle environment gives way to interstellar space. Then, in 2012, the readings changed violently. On August 25, particles associated with the sun dropped to extremely low levels. At almost the same moment, galactic cosmic rays surged. These were strong signs that Voyager had crossed the heliopause. But one expected clue refused to cooperate. The magnetic field did not rotate dramatically. Its strength changed, but its direction remained surprisingly similar to what Voyager had measured inside the heliosphere. That contradiction created a real scientific debate. Had the spacecraft actually crossed into interstellar space, or had it entered some unexpected boundary layer still connected to the sun? Think about what that means. Humanity had sent its first probe to the edge of the solar wind, and when it reached the supposed exit, the doorway did not look like the doorway predicted by the map. The particle evidence said outside. The magnetic geometry looked uncomfortably familiar. Scientists needed another measurement. They needed density. Plasma is often called the fourth state of matter. It is a gas in which some electrons have been separated from atoms, leaving a mixture of electrically charged particles. Stars are made of plasma. The solar wind is plasma. Much of the thin material between stars is plasma. The density of that plasma matters because the region outside the heliopause should contain more electrons than the thinned-out solar wind environment near the boundary. Voyager 1 carried a plasma wave instrument that could infer electron density from the natural oscillation frequency of the plasma around it. The basic idea is surprisingly intuitive. A wine glass has a characteristic ring. A guitar string has a pitch set by its tension, length, and mass. A plasma also has a natural frequency, and that frequency depends on how many free electrons are present. Higher pitch, higher electron density. But there was a problem. Voyager 1's direct plasma instrument had stopped functioning effectively decades earlier. The spacecraft could not simply scoop up the surrounding particles and count them in the usual way. So, researchers had to wait for the medium itself to ring. In March 2012, the sun produced a powerful series of eruptions. The resulting disturbance traveled outward through the solar system. More than a year later, in April 2013, it reached the region around Voyager 1 and compressed the plasma there. The plasma wave instrument heard an oscillation. Its frequency revealed a density far higher than the spacecraft had experienced inside the heliosphere. Researchers led by Donald Gurnett reported the result in Science in 2013. Combined with the particle changes from August 2012, the density measurement confirmed the historic crossing. Voyager 1 had entered interstellar space. But none of that prepared anyone for what it found next. Now the story gets stranger. At first, the plasma oscillations appeared only occasionally. They arrived when large disturbances from the sun pushed through the outer boundary and excited the surrounding electrons. Voyager would hear a burst, scientists would calculate a density, and then the signal would fade. It was like trying to map an ocean using only the sound of rare storms. Useful, but incomplete. The shocks appeared at irregular intervals, often roughly separated by months or longer. Each event gave researchers a point on the map. Between those points, the details vanished. Then, Stella Koch-Ocker, working with James Cordes, Shami Chatterjee, Donald Gurnett, William Kurth, and Stephen Spangler, went searching below the obvious signals. Ocker examined data from Voyager 1's plasma wave system, filtering out interference and looking for weak structures buried close to the instrument's noise floor. Instead of focusing only on the loud, short-lived whistles produced around passing shocks, the team searched for something steadier. They found it. Beginning around 2017, the data contained a very weak, narrowband plasma wave emission. In plain language, it looked like a thin line at a nearly single frequency, continuing through the gaps between the louder events. It was not perfectly constant. The pitch drifted over time. And that was the important part. Because the frequency was linked to electron density, the drifting tone acted like a moving density gauge. As Voyager traveled, the hum revealed how the interstellar plasma changed along its path. The result was published in Nature Astronomy in 2021. This was not a recording of sound traveling through empty space in the ordinary human sense. Voyager was measuring oscillations in charged particles and converting the electrical behavior into data. When those frequencies are translated into audio, they can be heard as tones. But the scientific discovery lives in the plasma, not in air, no microphone, no cosmic choir, a physical vibration in an ionized medium. That distinction makes the result more remarkable, not less. The team reported that the persistent emission allowed them to sample the plasma density steadily over a stretch of about 10 astronomical units, with an average sampling distance of roughly 0.03 of an astronomical unit. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. So a sampling interval of 0.03 astronomical units is still roughly 4.5 million kilometers. That sounds enormous. But for direct measurements in interstellar space, it is astonishingly fine detail. Imagine trying to map the texture of an entire continent while flying over it once, in darkness, with one narrow instrument pointed downward. Now imagine improving your measurements from one reading every few countries to one reading every few cities. That is the scale of the change. The hum turned scattered snapshots into something closer to a continuous line. And that line exposed another contradiction. Interstellar space was not smooth. It contained density fluctuations on scales comparable to the distance between the Sun and Earth. The surrounding plasma rose and fell in subtle structures, revealing turbulence. Turbulence is familiar on Earth. You see it in smoke twisting above a flame, cream folding into coffee, clouds curling around a mountain, or water breaking behind a boat. In each case, energy moves through a fluid in complicated patterns, creating swirls within swirls. Interstellar plasma behaves differently from ordinary air or water because magnetic fields and charged particles are involved. But the core idea remains. The medium contains structure across many scales. The supposed emptiness between the stars is textured, it has gradients, it has waves, it has turbulence. Still thin, still dark, still almost beyond comprehension, but not still. The third major finding deepened the mystery. As Voyager moved beyond the heliopause, the electron density did not merely jump once and settle immediately into a fixed interstellar value. Measurements showed that the density increased after the 2012 crossing. NASA's analysis of the persistent emission indicated that the electron density around Voyager rose from 2013 until roughly the middle of 2015, reaching levels about 40 times higher than those near the inner side of the boundary measurements being compared. Then it remained in a broadly similar range, with fluctuations. Why would the density continue rising? One possibility is that the heliosphere compresses the nearby interstellar medium, creating a denser region just beyond the heliopause. Picture a boat moving through water. Even before the hull physically reaches a patch of water, the motion of the boat changes the flow around it. Material can pile up, bend, and move around the obstacle. The heliosphere is not a solid hull, and the sun is not simply moving through a motionless sea. The real interaction involves magnetic fields, ionized particles, neutral atoms, solar cycles, and the motion of the solar system through the local interstellar environment. But the analogy helps. The boundary may not be a razor-thin skin. It may be surrounded by a disturbed outer region where interstellar material has been compressed, heated, redirected, and magnetically altered by the presence of the heliosphere. Researchers sometimes refer to the area just outside the heliopause as the very local interstellar medium. Voyager is not sampling some untouched average piece of the Milky Way far from all influence. It is sampling the neighborhood where the sun's bubble meets the surrounding cloud. That matters because the probe is both outside and still close to the edge. Interstellar, yes. Completely free from the sun's influence, no. And here is the fourth twist. The sun can still touch it. Large solar eruptions launch disturbances that move through the heliosphere. By the time those disturbances reach the outer solar system, they have expanded, merged, slowed, and changed. Yet, some remain strong enough to cross the heliopause and continue into interstellar plasma. Voyager 1 has detected shocks of solar origin beyond the boundary. Stop and sit with that. The spacecraft crossed out of the heliosphere in 2012, but years later, events that began near the sun could still travel outward, pass through the edge, and shake the plasma around Voyager strongly enough for the probe to detect the response. The sun's particle bubble has an edge. The sun's consequences do not stop cleanly at that edge. This helps explain the louder plasma oscillation events. A traveling shock compresses and energizes the plasma. Electrons begin oscillating near the local plasma frequency. Voyager's antennas detect the electric field changes. Scientists use the frequency to infer density, but the persistent hum is different. It continues between many of those dramatic shock events. Its exact physical origin is still not fully settled. The 2021 Nature Astronomy study discussed possible mechanisms including thermally excited plasma oscillations and quasi-thermal noise. That may sound intimidating, so strip it down. Even when no major shock is ringing the plasma like a bell, random motions and weak electrical fluctuations in the surrounding electrons may produce a background signature. Voyager's long antennas and sensitive receiver may be detecting that natural electrical murmur. Another possibility is that weak energetic electron populations or subtle wave processes help sustain the emission. They know the frequency tracks density, they know the emission is weak and narrowband, they know it persisted through the analyzed data beginning in 2017, they know it connects information between the louder shock-driven events. What remains uncertain is the precise engine producing it. That is how real science often looks. Not ignorance, resolution, a clear measurement opening a more precise question. Here is the part that stops being abstract and starts being personal. You live inside the structure Voyager is mapping from the outside. Every breath you take, every satellite you use, every power grid on Earth, every astronaut in orbit, every strand of DNA in your body exists within a space environment shaped by the Sunday. The heliosphere surrounds the planets and changes how charged particles from the galaxy enter the solar system. It is not a perfect shield. High-energy cosmic rays still reach Earth. Our planet's magnetic field and atmosphere provide additional protection, but the heliosphere influences the particle environment through which the entire solar system moves. And that environment is not permanent. The sun travels through the Milky Way. Over immense spans of time, it passes through interstellar regions with different densities, temperatures, magnetic fields, and neutral gas content. The shape and size of the heliosphere can respond. Imagine a soap bubble carried through changing wind. The bubble deforms, one side compresses, another stretches, the surface shifts. Now replace the soap with plasma and magnetic fields. Replace the wind with the local interstellar medium. Place every planet you have ever known inside. That is your cosmic address. Voyager's measurements help scientists understand the current boundary conditions around that address. How dense is the nearby plasma? How turbulent is it? How does the solar wind transfer energy into the surrounding medium? How do shocks cross the heliopause? How sharply does the environment change? These questions connect to how stars interact with their galactic surroundings. Other stars blow winds and create astrospheres of their own. Some host planets. Some of those planets may depend on magnetic and atmospheric protection while being exposed to cosmic radiation and stellar eruptions. Voyager is not measuring habitability around an exoplanet directly, but it is giving us the only in-place measurements from beyond a star's wind bubble that humanity has ever obtained. One star, one boundary, one tiny machine, and through it, a first lesson in how planetary systems touch the galaxy. Now let's talk about what is happening right now. Voyager 1 remains active, but the mission is living on borrowed power. Its 3 radioisotope thermoelectric generators produce electricity from heat released by the decay of plutonium-238. That power source has weakened gradually every year. Engineers have spent decades turning off heaters, instruments, and backup systems to preserve the most valuable science for as long as possible. In November 2023, Voyager 1 began transmitting unusable science and engineering data. The radio signal itself remained steady, but the information had become a repeating pattern. Engineers traced the problem to the flight data subsystem, including a section of memory that could no longer be used. The solution required the kind of patience almost no modern technology demands. A command needed nearly a day to reach the spacecraft. The response needed nearly another day to return. There was no reset button within reach, no technician beside the machine, no replacement computer waiting in a cabinet. The team reorganized software code, distributing functions around the damaged memory, and sending updates across interstellar distance. By June 2024, Voyager 1 had resumed returning science data from its operating instruments. That recovery mattered because every month of data is irreplaceable. No newer probe is close to the heliopause. No rescue mission can arrive. No duplicate spacecraft can be launched today and reach Voyager's location within a human career using ordinary mission designs. Then the power decisions became even harder. On February 25, 2025, engineers switched off Voyager 1's cosmic ray subsystem to conserve electricity. That instrument had helped measure energetic particles from the sun and galaxy and had played a central role in identifying the heliopause crossing. On April 17, 2026, NASA shut down Voyager 1's low-energy charged particles experiment. It had operated almost continuously since launch, turning on a scanning platform once every 192 seconds for decades, millions of mechanical movements in deep space. After that shutdown, NASA reported that Voyager 1 still had two science instruments operating, the magnetometer and the plasma wave system. The instrument connected to the strange interstellar hum is now one of the spacecraft's final scientific senses. No exact public date can guarantee when it will fall silent. Engineers continue managing power, temperature, communications, and aging hardware. The mission may continue for years, but every instrument shutdown narrows what Voyager can tell us. That is the ticking clock. The hum may persist in interstellar space long after the spacecraft is gone. Our ability to hear it will not. Picture the chain. Electrons drift in the darkness beyond the sun's bubble. Tiny fluctuations ripple through the plasma. Two metal antennas on a spacecraft launched in 1977 sense the electrical motion. A transmitter sends a signal toward a star that now looks like one bright point among many. Giant antennas on Earth collect power so faint that ordinary background noise could overwhelm it. Engineers decode the stream. Scientists turn frequency into density, and a hidden structure in interstellar space becomes measurable. Every link is fragile. The plutonium cools, the electrical supply falls, components age. The signal weakens with distance. Still transmitting, still measuring, still moving, for now. Voyager 1 travels outward at roughly 3.5 astronomical units per year. It is not heading toward another star in any practical mission sense. In tens of thousands of years, it will pass within a few light years of another star, but no encounter will occur soon enough for the spacecraft to report back. Its active scientific future is much shorter. That creates an uncomfortable contrast. Voyager's journey will continue for geological ages, but its voice belongs to this moment. The machine may wander through the galaxy long after human languages have changed, coastlines have moved, and every living person has been forgotten. Yet the period when it can still send measurements home is measured in years. Not centuries, years. Future interstellar probe concepts could carry vastly better instruments, higher data rates, and dedicated systems for studying the heliopause and the surrounding medium. But such missions would require long planning, enormous endurance, and decades of travel. Voyager remains alone at the frontier it discovered. So each new plasma measurement has two meanings. It is a scientific data point, and it is part of a closing record. Here is what I want you to take away from all of this. The space between stars is not empty. It is quiet enough to hide structure, but alive enough to reveal it. That is the repeatable truth. Quiet is not the same as nothing. Voyager 1's weird finding is not frightening because it suggests something impossible. It is powerful because it reveals how much reality can exist below the level of ordinary perception. A tone too faint to notice. A density change spread across billions of kilometers. A shock that began near the sun and arrived years later. A boundary crossed without the magnetic turn scientists expected. None of these facts announces itself with an explosion. They emerge slowly, through careful comparison, patient engineering, and instruments that were never supposed to remain useful this long. There is humility in that. For most of human history, interstellar space was an idea, a black interval between stars. Then it became a region telescopes could study indirectly through absorption, radio scattering, and the behavior of distant light. Now, for the first time, it is also a place we have touched. Not visited with people, not crossed with a fleet, touched by one aging machine. Voyager cannot see the interstellar medium the way a camera sees a cloud. It senses charged particles, magnetic fields, and waves. From those fragments, scientists build a picture. And the picture is dynamic. The heliosphere presses into its surroundings. The surroundings push back. Solar disturbances cross the boundary. Plasma density changes. Turbulence folds through the medium. The galaxy begins not at some distant star, but immediately outside the bubble surrounding our own. That may be the most haunting part. Interstellar space is not far away in the way we usually imagine. Its boundary is far beyond the planets, yes, but cosmically, it is our doorstep. Voyager 1 is standing just beyond it, listening. So, when you picture the spacecraft tonight, do not imagine it sailing through perfect emptiness. Imagine it moving through an invisible, electrically charged ocean thinner than any vacuum humans can easily create, crossed by magnetic fields, shaken by ancient stellar processes, and still disturbed by storms born from our own Sunday. Imagine two antennas stretching behind a small metal body. Imagine the faint line in the data. Imagine the pitch changing as the density changes. The darkness has texture. The silence has a signal. And for a little longer, we can hear it. Subscribe for more factual deep space stories and turn on notifications so you do not miss the next discovery hidden in old mission data. In the comments, tell me this. If you could keep only one Voyager instrument alive, would you choose the plasma wave detector or the magnetometer? Share this with someone who still thinks space is simply empty. More than 25 billion kilometers away, the wine glass is still ringing in the dark. Thanks for watching.